Hello, I'm glad to see you again. And let's start our lecture on avionics engineering. Today, we have lecture number 14 as the topic terrain reference navigation. You know, TRN or terrain reference navigation is a generic classification which covers any technique of aided navigation, which relies on correlation terrain management data from a suitable terrain sensor or sensors with the data stored in a digital map database. So the system is operated in conjunction with dead recorded navigation system. The position fixes derived by the TRN system are then used to update and correct the direct recording, dead recording system errors by means of Kalman filter. The TRN system can only be used over LAN and require a very accurate database. The latter may need to be derived from satellite data when accurate map data are not visible. So terrain reference navigation systems can be delivered into three basic types. First, terrain contour navigation, TCN. In this system, the terrain profile is measured by a radio altimeter and is matched with the stored terrain profile in the vicinity of the aircraft's position, as previously estimated by the dead recording navigator. Second, terrain characteristic matching, TCM. This type of system can use a variety of sensors, like radar or radiometric sensors, to sense changes in the terrain characteristics below the aircraft. For example, flying over lakes, rivers, roads, woods, buildings, and many others. The data can then be processed to detect the edges or even boundaries where the terrain characteristics change abruptly. The detected edges of the overflown features can then be matched with the stored terrain features in the vicinity of the aircraft estimated position. So, both TCN and TCM can be used in a complementary manner. TCM providing very good positional fixes where there are reasonable terrain contour variations. Over very flat terrain, the TCM accuracy is degraded. However, the TCM system can then provide very good positional fixes from the detected edges of specific terrain features. And third, thin matching area correlation, FMAC, thin matching area correlation. This is also known as digital thin matching area correlation in the USA. These systems generally used in infrared imaging sensor to locate and lock on to specific recognizable landmarks or set of features at known position on the route. An area correlation technique is used to match the proceed image data with the stored feature data, so that the system will track and lock on to the feature. The aircraft position must be known accurately in the first place using, say, TCM. Okay? So let's back to our slide. And now let's continue. The order of magnitude accuracies which can be achieved with these systems are TCM around 50 meters, TCM around 10 to 20 meters, SMAC around 1 up to 2 meters. But it should be noted that while the basic concepts of this TRN system are relatively straightforward, there is a very considerable mathematical content involved in explaining the detailed implementation of these systems. For example, statistics, probability theory, correlation techniques, state estimation methods, and even common things. Space constraints have therefore limited to the coverage of TRN systems to a brief overviewing form. So let's start with terrain contour navigation. The basic concepts of terrain contour navigation are illustrated in the next figure. Look this one. The three types of measurement data are required by the system. First, a sequence of measurements of the ground clearance. Another thing, high above the ground level of the aircraft. This is normally obtained by sampling the output of radio altimeter, possibly with some additional pre-filtering. A horizontal sampling interval of about 100 meters is typically used, but this is not critical generally. Second, data from a barometric or baro-inertial height system is required to measure any vertical motion of the aircraft between successive ground clearance measures. And third, some form of TR navigation system like INS or Doppler radar plus hidden reference is required to measure the relative horizontal positions of the ground clearance measurement. The essence of TCM is to use this data to reconstruct the terrain profile under the aircraft threat. A digital map of terrain height is then searched to find a matching profile in the vicinity of the aircraft's position as previously estimated. And this can then be used as the basis of an update to the estimated position. There are a considerable number of TCM implementations which have been developed in the US and Europe to provide very accurate navigation systems such as TERCOM, TERFA, CITAN, CA Road, TERPROM, Spartan. Now, let's start another subtopic today's lecture, terrain characteristic matching. The edge detection of specific terrain features has been mentioned earlier in this module. I hope you remember, okay? The basis of the technique is shown in this figure, which shows a sequence of position likelihood distribution which indicate how the position estimate improves the feature boundaries are detected. That I think it's not difficult, very simple, okay? Let's go now. It should be noted that while TRM, means terrain reference navigation, right? Systems have been used in exclusively military applications today. They can clearly be exploited in civil aircraft as very accurate self-contained navigation aid, particularly in the terminal area. Accurate radio altimeters are installed in most civil aircraft together with accurate TR navigation systems such as IN systems. The TRN computer and terrain database is a modest equipment increment with current electronic technology. And now, let's start another main topic for today's lecture. It's called air data and air data systems. You know, air data systems provide accurate information on quantities such as pressure, altitude, vertical speed, calibrating airspeed, true airspeed, Mach number, static air temperature, and air density ratio. This information is essential for the pilot to fly the aircraft safely and is also required by a number of key avionics subsystems, which enable the pilot to carry out the mission. It is thus one of the key avionics systems and forms part of the essential core of avionics subsystems required in all modern aircraft, civil or military, no matter. And this lecture explains the importance of air data information and shows how the fundamental physical laws are derived. And the air data quantities are generated by an air data computing system. So let's start with air data management. The air data quantities, pressure, altitude, vertical speed, calibrated airspeed, true airspeed, Mach number, etc., are derived from three basic measurements by sensor connected to probe, which measure total or pitot pressure, static pressure, total or indicated air temperature. Figure on this slide illustrates a basic air data system. The total pressure P sub T, yes, is measured by means of an absolute pressure sensor or transducer connected to a pitot tube facing the moving airstream. This measures the impact pressure Q sub C, and that is the pressure exerted to bring the moving airstream to rest relative to the pitot tube plus the static pressure. Static pressure PS, P sub S, yes, static pressure as we have here. Or the free airstream, so that we may write as PT is Q sub C times PS, right? This static pressure or free stream airstream, or P sub S, yes, is measured by an absolute pressure transducer connected to a suitable orifice located where the surface pressure is nearly the same as the pressure of the surrounding atmosphere. High-performance military aircraft generally have a combined pitot static probe, which extends out in front of the aircraft so as to be as far away as practicable from aerodynamic interference effect and shock waves generated by the aircraft structure. Some civil transport aircraft have pitot probes with separate static pressure orifices located in the fuselage, generally somewhere between the nose and wing. The exact location of the static pressure orifices and the pitot tubes or probes certainly is determined by the experience and experimentation. However, many civil transport aircraft like Boeing 747 have side-mounting, so-called L-type pitot-static probes. The trend of new military aircraft is to use flash port system for stealth reasons, protruding probe gives a significant radar return. It is interesting to know that the pitot tube, which is universally used on aircraft and in wind tunnels for measuring airspeed, because of its simplicity and effectiveness, was invented over 250 years ago by the French mathematician and scientist Henri Pitot for measuring the flow of water in rivers and canals, one invention which has stood the test of time. From the measurements of static pressure P sub S and total pressure P sub tau T, it is possible to derive the following quantities. First, pressure altitude, HP, pressure altitude. This is derived from the static pressure P sub S measurement by assuming a standard atmosphere. Vertical speed, HP. This is basically derived by differentiate T sub S, calibrated at airspeed V sub S, T, sorry. This is derived directly from the impact pressure QC, which is in turn derived from the difference between the total and static pressure. I hope you remember. QC equals P sub T minus P sub S. Okay? And Mach number M. This is the ratio of the true airspeed V sub T to the local speed of sound. Local speed of sound is A, like a capital A. That is Mach number equals V sub T over A, and is derived directly from the ratio of the total pressure to the static pressure, or P sub T over P sub T over PS. True airspeed is defined as the speed of the aircraft relative to the air, right? The third measurement, namely that of the measured or indicated air temperature, T sub M, is made by means of a temperature sensor installed in a probe in the airstream. This gives a measure of the free airstream temperature, T sub F, plus the kinetic rise in temperature due to the air being brought partially or wholly to rest relative to the temperature sensing probe. The temperature assuming the air is brought totally to rest. So say recovery ratio in our case should be equal 1, and is known as the total air temperature T sub T, total air temperature. The computation of the aircraft's Mach number M, together with the known recovery ratio of the probe, which allows for the air not being brought wholly to rest, enables the correction factor for the kinetic heating effect to be derived to convert the measured or indicated air temperature to the free stream or static air temperature T sub F. The static air temperature so derived then enables the local speed of sound A, I hope you remember, to be determined, as this is dependent only on the air temperature. True airspeed, V sub T, can then be readily computed like V sub T equals Mach number M times A, speed of sound. Air density ratio, rho over rho naught, can then be computed from P sub S and T sub S, because rho is air density, and rho naught is air density at standard sea level condition. Okay? Nice. Next topic, the air data quantity. The use and importance of the air data quantities of pressure, altitude, vertical speed, rate of climb or descent, calibrated airspeed, Mach number, and true airspeed by the pilot and the key avionics subsystems is discussed in this module. Okay? So let's start with the air data information for the pilot. Pilot is presented with displays of the above air data quantities, all of which are very important at various phases of the flight or mission. However, the two basic quantities, which are fundamental for the piloting of any aircraft, from a light aircraft to a supersonic fighter, are the pressure altitude and certainly the calibrated airspeed. So, pressure altitude is the height of the aircraft above sea level, derived from the measurement of the static pressure, assuming a standard atmosphere. Calibrated airspeed is the speed which, under standard sea level conditions, would give the same impact pressure as that measured on the aircraft. The altimeter displaying pressure altitude and the calibrated or indicated airspeed display, and thus form part of the classic T layout of vital instrument displays centered around the air artificial horizon display. This layout has been largely retained for the modern electronic displays. The use of the air data information by the pilot is discussed now. So, calibrated air speed. What I say? I can say that the reason for the importance of calibrating airspeed information is that it provides a direct measure of the impact pressure by definition. And the impact pressure, together with the angle of incidence, determines the aerodynamically generated lift and drag forces and moments acting on the aircraft. By the way, the angle of incidence is the angle between the direction of the airflow and a datum line through the airfoil section of the wing or control surface. These aerodynamic forces and moments in turn determine the aircraft's ability to fly and maneuver, its controllability and response, and its performance in terms of speed, range, operating height, etc. The impact pressure is a function of the true airspeed, V sub T, and the air density rho, and at low airspeeds up to about 100 meters per second, or nearly 200 kilonauts, the compressibility effect, and can be neglected, is equal to 1/2 times rho times V times T squared. This relationship no longer holds as the speed increases and compressibility effect increases, and the impact pressure becomes a function of Mach number as well. The air density is directly related to the altitude, so that to maintain the same lift force at high altitudes at the sea level and requires an increase in the true airspeed to produce the same impact pressure. And hence, the critical speeds which affect the aircraft behavior, controllability, or safety are specified in terms of calibrated airspeed, and this is independent of the air density variation with altitude or temperature. Such critical speeds include the rotation speed for takeoff, the stalling speed, and the not to exceed speed in a dive when the aerodynamic forces and moments exerted during the pull out and would approach the structural limits of the airframe. or the controllability limit would be reached. But it should be noted that the quantity indicated airspeed is frequently used in this context. The indicated airspeed is basically the same quantity as calibrated airspeed, but includes the pressure error present in the pitot or static installation, and the instrument error present in a simple mechanical type of airspeed indicator. Airspeed indicator is ASI instrument. You know, calibrated airspeed is derived by the air data computer using very much more accurate pressure sensor and the inherent pressure errors in the pitot or static probe installation and can be compensated by the computer. Pressure altitude, accurate measurement of the aircraft altitude, is essential for the control of the flight path in the vertical plane. For instance, to maintain adequate clearance of mountains and hills, and etc., under conditions of poor visibility, flying in cloud or at night. So in this case, altitude and airspeed are also wider displays during the approach and landing. The air traffic control, ATC, authorized also required very accurate measurement of the pressure altitude for air traffic control to ensure safe vertical separation in busy airways. Pressure altitude is therefore automatically reported to the ATC, air traffic control ground control, by the ATC transponder, as will be explained in next module. The ATC, or air traffic control, also require that the reported pressure altitude must be the same as that displayed on the pilot's altimeter display. Through airspeed, this information is displayed to the pilot for navigation purposes. Mach number, as the aircraft speed increases and approaches the speed of sound or exceeds it in the case of a supersonic aircraft, there is a large increase in drag and lift characteristics change, and the pitching moment characteristic change due to the compressibility effect. The performance and controllability over the aircraft is dependent on the aircraft's Mach number in this high-speed region. Accurate information on the aircraft's Mach number is thus an essential display for the pilot. It is also essential information for other aircraft systems, which are discussed a bit later today. Right? Let's go. Vertical speed or rate of climb or descent. A display of vertical speed or rate of climb or descent is also required by the pilot, and this quantity is generated within the air data computer by differentiating the static pressure. Rate of descent is particularly important during a ground control approach, GCA, where the pilot will set up a given rate of descent and speed certainly in the approach to the airfield. The vertical speed indicator, VSI, vertical speed indicator, display is also used during a turn to detect any tendency to lose sky. The pilot applying appropriate corrective movements to the control column or stick to hold a constant high turn. Angle of incidence. The importance of the angle of incidence has already been mentioned. But generally, the lift force from the wing increases linearly with increasing incidence angle up to near the maximum permissible incidence angle, at which point the airflow starts to break away, and further increase would result in the wings stalling with consequent sudden loss of lift. Airflow sensors to measure the angle of incidence are thus frequently installed, and so that the pilot can monitor the situation and ensure the critical value is not reached. But it should be noted that the term angle of attack is generally used in the USA for angle of incidence. Okay, you remember this. Okay, our next topic, air data for key subsystems. The key subsystem requiring air data information and their use of this information. And I hope we now briefly describe this in this slide. Air traffic control transponder. Pressure altitude is supplied to the air traffic control ATC transponder for automatic reporting to the air traffic ground control system. The ATC, or air traffic control, authorized specifies the flight levels which aircraft must maintain in control airspace in terms of pressure altitude, and these are set so that there is a minimum of 1,000 feet vertical separation between aircraft flying in the vicinity of each other. As stated earlier, pressure altitude is derived from the measurement of the static pressure and the assumption of a standard atmosphere, which enables a unique mathematical law to be derived relating altitude to the static pressure. Pressure altitude, however, can differ from the true altitude because of the day-to-day variations from the standard atmosphere. These differences are small at low altitudes if the ground pressure correction is applied, but can be much larger at higher altitude. This difference between pressure altitude and true altitude does not matter from an air traffic control standpoint, providing the pressure altitude measurements are sufficiently accurate. This is because the difference is common to all the pressure altitude measurements made in the vicinity of each other. For example, suppose aircraft A is given a flight level of 33,000 feet to fly by the ATC authorities, and aircraft B is given a flight level of 34,000 feet. So let the difference from the true altitude be delta H. Yes? So that ignoring any error is the pressure altitude measurement in the two aircraft. So the true altitude of aircraft A will be 33,000 plus delta H, and the true aircraft for B will be 34,000 plus delta H. Okay? The required vertical separation of 1,000 feet is maintained. The cruising altitudes of jet airliners are typically in the 29,000 up to 45,000 feet, as you can see from this part of the slide. And this band, and it will be shown a bit later, as that the ATC 1,000 feet separation levels place very stringent accuracy requirements on the static pressure sensor. Flight control systems, calibrated airspeed and pressure altitude information is required by the flight control system, FCS. This is to enable automatic adjustment to be made to the gains or carrying of the FCS flight control systems with airspeed and height to compensate for the wide variation in the control effectiveness and aircraft response over the flight envelope. This is frequently described as air data gain schedule. Adequate redundancy must be provided in the system to ensure failure survival in the case of a fly-by-wire flight control system. This may involve 3 or even more independent air data computing systems. Autopilot system. A number of autopilot control modes require air data information. Another thing, height acquire a hold, Mach number acquire a hold, and airspeed acquire a hold. The same air throttle system. Air data gain scheduling may also be required by the autopilot control loop. Autopilots are covered in the future lecture. Navigation system. Pressure, altitude, and true airspeed are required by the navigation system. Pressure altitude is required for navigation in the vertical plane. It can be combined or even mixed with the inertially derived information from the Inertial Navigation System INS to provide vertical velocity and altitude information, which is superior to either source on its own. The aircraft's velocity vector is derived from the vector sum of the barometric or inertial vertical velocity and the horizontal velocity or ground speed vector. Output from the INF. The velocity vector information is used for guidance and control. Another say HUD, flight director system, weapon aiming system, etc. Pressure altitude is also essential information for a terrain reference navigation, TRN, terrain reference navigation system, as it measures the vertical motion of the aircraft and so enables the ground profile to be derived from the radio altimeter measurement. TRN system, terrain reference navigation system, operate by correlating the radar altimeter measurements of the ground profile with a stored topographical map elevation database and hence establishing the aircraft position and correction the TED recording position estimate. By the way, it is interesting to note that the standard deviation from the horizontal of an isobar is a line joining points of equal pressure, over a distance of 1 nautical mile at sea level is 1 on. True airspeed is required for dead recording DR navigation. Dead recording or DR position being computed from a knowledge of the true airspeed, aircraft heading, and forecast estimated wind velocity. True airspeed information is also used to compute the wind velocity vector using the ground speed information from the INF. Other sources of navigational information, like GPS or Doppler, can also be used to derive wind velocity from the true airspeed information. Information on wind velocity is required by the Flight Management System, FMS, as will be explained in a couple of minutes. So, wind velocity information is also required for weapon aiming in the case of a military aircraft. Flight Management System. The Flight Management System requires information on all the data, air data quantities, pressure, altitude, vertical speed, Mach number, static air temperature, true airspeed, and calibrated airspeed. Air data information is essential for the FMS to maintain the aircraft on the most fuel-efficient flight path and for achieving 4D flight management. why we speaking about 4D flight management? We mean 3D position and plus time, right? So in this case, we have the 4D flight management and FMS system are covered in earlier lectures. I hope you remember. And engine control systems, high and calibrated airspeed information is required by the engine control systems. The flow of air data information from the air data computing system to the key avionics subsystems is shown in this slide. Modern aircraft systems use a time multiplex system, digital data bus system, such as MIL-STD, 1055 and 53B on a military aircraft, or ARING 629 in the case of a civil aircraft to transmit the data and interconnect the system. The degree of redundancy has been omitted for clarity. For instance, civil aircraft have at least two independent air data computing systems. But I think it's enough for today. Let's continue next time. And I think I hope you enjoyed this lecture. And as usually, I'm looking forward to seeing you next time. Bye.